Hey everyone, how are we doing? I got my second cup of coffee. Who is all here? We did some review during class day. We had a big Kahoot. We had a big winner. Congratulations. And congratulations to second prize. Second place emailed me. I'll be sending that out. Third place emailed me too. We know who first place is. I'll email them probably and say, hey, where do you want me to send it to? All this good stuff right here. I'm just looking at the emails right now for the moment. If you have questions, let me know. Got references. Good stuff. Mini-term grades are open. Statistics, all that good stuff. Probably those layers. Guten Morgen, Mr. Ryan. Good to see you here, Cad. What questions do you have, Cad? Which one are you working on? What questions do you have? If you have any questions, let me know. Let me know. We'll work on it. We'll talk about review stuff. Let's see. Has anyone else taken the exam right now? I can't say grades, but I'm interested to know if people have been taking the exam. Let me send out a reminder to the class. And Cad, good to see you here. I'm going to send out a reminder that the exam is due tonight by midnight. So let's send an announcement. Go to announcements plus announcements. Exam reminder. Exam 3 reminder. Exam 3 is due tonight by 11:59 p.m. The review material are the formula sheets. The exam can be found on the review page. Let's go right here and let's go grab the review page. Mubot knows where that's at. So let's go here to review material exam 3. Go take this right here. And click here. Best way to tell people where to click. And there's that. Link inserted. There we go. Reminder sent. There we go. I have a question from the Canvas content quiz. Sure, Sophia, which one are you working on? I don't really have specific questions. I just want to do all the homework quizzes. I was here for review material. Yeah, Sophia, ask your question. Which question do you have? We just sent out that announcement. So Sophia, feel free to drop the question here in the chat. And we can work on that. Let's see. Second cup of coffee. My Pearson. Let's see. Sophia's going to drop the question in the chat. I'm getting the Canvas content up. And let's see. Has anyone else taken the test yet? Got 3 people taking the test. Good stuff. Good stuff. 3 people. How do I know 3? 4 people have taken the test. So 4 people have taken the test. 4 people have taken the test so far. 4 people have taken the test. We will be then putting, if you get higher on exam 3, remember that can go over to the exam, the previous exams. So make sure to have all the work, do the Canvas contents. Let's see the question here. Let me go away from that. For a difference of 2 means, is it from a table so I can't really write things out? Calculating the test statistic. So let's go ahead and preview this. Okay, let's hover the main screen. So the difference between 2 means. What does your question say to start? Is it this one? Is it is it want you to calculate the test statistic, right? Okay, let's generate a version that has the test statistic and talk about how to calculate that. So we need to find a version that has the test statistic on here. So we're going to find one with the test statistic. Surely we can find the test statistic. Wait, see here. It's not that one. Okay, good. Where is it? Where are you, random question? We'll give it a few more tries right here to find it. So we're just trying to find that random question which has a test. Oh, I think this is it right here, right? So it wants the t ratio, which is the test statistic. So the t ratio there is the test statistic, and I think we found it. Oh, review. I keep doing review 4. Yes. Okay, so when we do this right here, the test statistic is going to be, and I'm going to take a big screenshot right here so I can draw on this. The test statistic is going to be, and let's figure out how to find this. This t ratio right here is going to be the y bar 1 minus y bar 2. So the formula sheet is right there with review test 3. This is y bar 1. That is what the t statistic will be for this. The t will be y bar 1 minus y bar 2. So do you notice any of this anywhere on here, Sophia? Do you notice any of this information? So the t ratio, the t statistic, is, let's look right here. Do you notice this anywhere? That's y bar 1, which is minus y bar 2, which is the sample mean 1 of group 1 minus the sample mean of group 2. So that's the difference between the sample means. Do you notice that anywhere? Is that value anywhere on this output? Can we find that value right here? Is that value anywhere on this output? So we got y bar 1 minus y bar 2, which is mean 1 minus mean 2, because the y is the observation, the mean of the observation, group 1. So this just stands for like y is like a variable, mean of that variable, because we put a bar on top to mean mean. And do we see this anywhere on here? Do we see this anywhere? Where do we notice this right here? Well, that's close. Good guess right there. Good stuff. I'm gonna throw some 20 points right there. That is gonna be the difference. Explicitly looking at this right here, this is the difference. Does that make sense? Like that's the difference between the two means. So the difference between the two means is going to be that right there is the difference between the two means. So then think about what you would call this down here on the bottom of the equation. Since that's the difference, what do you think this is in terms of, and it's very similar to, it's not the same equation, but it's very similar to s over square root of n, which for one mean is the standard error of the mean. So that's the standard error of the mean. Like s over square root of n is the standard error of the mean, but what do we have right here with s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2? So what does that become? That is the what for the difference between two means. That's also another version of a what. So what is that notation-wise? We'll make this a little more clear. We'll highlight a little bit better. So the bottom part of that equation is the what of the difference between the two means. The bottom part of that equation is the what of the difference between the two means. So what would the bottom part of the equation be? The bottom part. So what do you think the answer will be? I might leave it at this. I'll just put it in the chat if you want. Gotta make something even clearer right here. Yep, that's the difference between two means. Yep. Y bar 1 minus y bar 2. Yep. And that's the standard error right there. That's the standard error of the equation. Because the standard error of the difference is the bottom part. Like this right here is literally, I think you're seeing it now, right? Well, we won't divide it by 2. We won't divide it by 2. Because this down here on the bottom is literally just the standard error of the difference between the two means. So this is literally, like, I'm just changing what it's called down here. I'm not writing it in equation format. I think you're seeing it right. Yeah, I think you're seeing it right there. Yep. So that is the standard error. Like the standard error. Yeah, no worries. No worries. The standard error is this right here. That is the standard error, but like notation wise, like if you don't write it as the standard error, then it's written as that. Like that is the standard error. Like we would just call this whole thing right here. Maybe it is. I can't confirm or deny the answers. That whole thing right here is the standard error. Like that's what it's called. Like it's like putting this whole thing together. It's called the standard error. Does that make more sense, Sophia? So basically you're meant to kind of notice that this is the standard error. This is the difference. Dividing the difference by the standard error gives the t ratio. Oh, no worries. You can put answers in the, you're fine to do that. I mean, we're basically showing how to solve it. No, you're fine. Don't worry. You're doing a great job. I'm throwing another 50 points, Sophia. You're fine to ask these things. Don't worry. Yeah, that's what we want to see. The good practice right there of basically knowing how to read the output and what it all means. And we should know things about like how to tell how big this confidence interval is. So whenever you look at this output, one of the things I suggest to people all the time is like make sure it all makes sense. Like if I'm going to figure out how wide this confidence interval is, then I'm going to go right here and do the following and divide by 2. And you know what we should get? Yeah, it looks like it did it. If we take the margin of error right there, which we just found by upper minus lower divided by 2, we do get a little bit difference right there. So the standard error is the whole, yep, this is literally the standard error. Like this right here is the standard error. Like this thing right here is the standard error. I think the formula sheet also makes that clear. MuBot should have dropped the link right here. So once again, we can call the review for exam 3. I should put a timer in where MuBot tells people what his commands are. Like, you can ask me about this with this, or you can, use exclamation mark before any of these to ask about these things. So we go here to the formula sheet, and I think it also makes clear that the standard error, yeah, it says right here where the standard error is this. I'm not a big fan of, I usually just write that in on the bottom, but you can see the standard error is this right here. And so you just solve with the standard error. I guess the standard error is the same thing: s sub 1 squared over n sub 1, s sub 2 squared over n sub 2 square root of the quantity. So this right here, degrees of freedom are from the complicated formula. So, and we got the TDF for that. But ask more questions if you have them. Really good review of basically how to read jump output right there, which you can see similar relationships. If we pull up another jump output right here where we've done a 2-sample t-test, I think I just saw one. Here it is. The t ratio right here of 1.3 or negative 1.3 can be found by doing the following. We're just going to compute this t ratio right here just to show how to do it. 0.6881, and that's a negative. And then we divide by 0.5269, and we get the t ratio. And there's just some decimals going on in the background that we can't see, but we get negative 1.306, negative 1.306. And yeah, and this is a high p-value here, which denotes that we don't have evidence of a difference between the two means. All that good stuff right here in the formula sheet. More questions if you have them. More questions. Get everything set up. I think I could put a timer on here. I'm going to make this from MuBot right now. We're going to make a timer on MuBot. So, let's go new timer. And general. I have forgotten how to do this. Group. Right, add timer. Let me look at this one. Edit. Well, how quickly are these doing it? Settings. 2 seconds. Let me look at the settings. Okay, minimum chat lines 5. He does it every 5 minutes. There's one of these I've been thinking about removing. Remember to use Brian. Use points to check out your MuBucks. Check out the Stats1 website. That's good. I don't know. I'll work on this later. His timers, but all these different things. So many different moving components. I'm lucky that I've been doing this for a while because people say, well, how did you learn all this? And I say, I don't know. Each semester I just learn new things. I just make new things. Just a year ago, we made MuBot out of necessity. 1 year ago this August, he'll turn 1. MuBot, where are you at? He came into existence last semester. He took corporeal form. And then Evil MuBot came about, which is not totally covering up the... Oh, there we go. What questions do you have if you have them right now? Almost like that, a little bit of shadow around him. There we go. There we go. We got MuBot. We got Evil MuBot. I need to make the buttons for him to appear. We got to switch over to OBS eventually. There's lots of little things. Let's head back here to space while we wait for the next question. Here we go. Lots of moving components. Just working on it. And really, it's a lot of advice from students, a lot of help from students. They've given me a lot of advice. They've taught me a lot of things. It was a student a long time ago who taught me how to stream. Yeah, you want to do a practice exam question? Let's do it. Thank you, Sophia, for asking the questions. Let's go look at a practice exam question. You are here to ask the questions. I am here to answer them. So let's do it. Do you have a specific part of the practice exam, or do you just want me to start from the beginning? Like, I can start from the very beginning of the practice exam. We can go from there. Let's start doing some practice exam. That's a good idea right here. exam day, right? Let's do some practice exam. Okay, here we are with the practice exam. I'll disappear when I don't need to be on the screen. Below is the output from my hypothesis test from the beginning. You got it. I think I might be able to do this. Watch this. Oh. Yeah, we can't use the zoom for that. I guess because of this, right? Such a bummer, because that makes the screen uneven on me. Below is the output from a hypothesis test from a single population mean. So that's a one sample t-test. We'll probably take... Is that all it is for this question? Cool. Okay. Let's go ahead and grab this question, bring it over to Word. Because we're going to be able to draw on it a lot easier. Okay. Million word documents, 1,000,001. Okay, so now I can appear. Below is the output for a single proportion mean test. I'm immediately going to identify in this question we are doing one sample t. So this is going to be a t-test, which means one quantitative variable. It's one quantitative variable we analyzed. Based on 28 observations, I'm going to immediately identify that this is the sample size, which it's listed below. That is the sample size. The null hypothesized value as well as the sample mean actual estimate. So that's the sample mean. The hypothesized value is mu naught. It's hypothesized true mean. The degrees of freedom are blanked out and standard deviation is S. And we're given some values. So basically we just need to fill in the remaining values. We need to calculate the degrees of freedom. This is a one sample t-test. So it's a one sample. And so what are the degrees of freedom for the one sample t-test? We'll write some answers here in orange. The one sample t-test, put a few more notes. This is the less than p-value. This is the greater than, and I'm gonna draw a little graphic over here to show me. Less than, greater than, and we're missing the two-tail. So we're missing that one over here. Talk about that in a moment. 27 CAD, I believe you are correct. That is the degrees of freedom. Degrees of freedom are n-1. So the degrees of freedom for the one sample t-test, great job there, CAD, is n-1. So we have here that this is going to be sample size minus 1. We've already solved for that. So the degrees of freedom are 27. Put on my music, y'all. And with this right here, 27. Great work. And then we have here the test statistic. Ooh, that's a complicated one. The test statistic is y bar minus mu naught over S over square root of n. That's the one sample t. We've got the formulas, just so you can see if you identify what test is. We have the formulas over here on the following page. The one sample t formula is right here. Here's the hypothesis test for one mean. We just have a mean. So here's the formula y bar minus mu naught over S over square root of n. And that's why I've written out right here. That is the standard error. It's just standard error of y bar, but S over square root of n is what we put in. So we're going to go right here and go to 18.6286 minus 20. Why is there got to be so many decimals? And then S, which is 2.46484 over square root of 28. A bunch of way too many decimals on this. Way too many decimals. 28 square root 2.46484 divided by that. Copy that so we can keep it. Top number minus 20 divided by. Ooh, I like that. It's really interesting. It's really interesting because it's basically 3. I like this a lot. Negative 2.944. Makes sense with the p-values we're getting because I want you to think about something. When you have a z statistic, so just pretend this is the z curve. If you had a z curve of following, if you got -3 right here, which is about where we're at, we're not quite at that. And then if you were to plot something over here, and you were to have this at +3, which is something just as extreme, then outside of this curve, you'd have 0.15 on this side percent, or in a p-value sense, 0.0015. And over here, you would have 0.0015. Now, that's not the exact values we're getting, but that would round up to 0.02. And you can see that's about what we're getting for this one right here. which I'm shading right here. That's just kind of a small representation. Now, what would we get? How do we get this last p-value right here, which is an important thing to talk about? How do I get the last p-value, which is kind of, you can look at my graphic or you can look at their numbers. If you want to find the exact answer, which we should be finding, you want to look at this one. Or you can think about, here's the answer in yellow for me right now using an estimate. And then what would I do to get the actual answer up here, which maybe I'll do it. I'm going to draw it this way to color code the answer to help out. How am I going to get the two-tailed test right there? So I've kind of got some color coding here to help out. In truth, if I'm actually plotting this correctly, the way it's actually going to look with the results we have on the screen is going to be this and this. And now we want this area. And so here's graphically the answer. It's not using the normal curve anymore to make estimates. It's saying we fell at a t of negative 2.944 and something just as extreme as positive 2.944. So what would we do right here to get the two-tailed test? Because we have the less than test. The less than test is the area below this, as you can see via my mini graphic up here. And the greater than test is the area above it. So good question, Cad. Double check here. We'll double check that real quick to Cad's question, then we'll look at the last one. Yep, and Cad, you got, I think, I know what you're gonna put right there. Cad's gonna put it in half a second. I think Cad sees how to get the other one. The bottom of the equation, check your bottom of the equation. The bottom of the equation is your bottom of the equation this? That might be where the error is. Check to make sure your bottom of the equation is 0.465. Don't delete any decimals till the very end. I carry all decimals till the very, very end. Is the bottom of your equation this? That's probably where the error is at. Maybe you're not square rooting 28. That might be it. You might not have square rooted 28. Maybe square rooted this afterwards. No, I wouldn't do it. Yeah, that's what it, because the top part of the equation is the easy part. The bottom part's usually where the mistakes happen. So you should get negative 2.949. Great job, Cad, right there. Good practice. And then Cad noticed that all we're doing right here on the bottom part is we are just squaring. This. I got it. Nice job, Cad. Great work. Let's throw some 50 points out there. Practice, practice, practice. There are some good grades on the exam right now. There are some really, I put it in all. Yeah, I do it in parts every time. I'm going to drop my pen. Classic. I do it in parts every time. I'm always like, okay, let's do a part of this. And we're just doubling the smaller p-value, which we didn't do properly. There we go. That's got it. We doubled the smaller p-value. Excellent work right there. I was square rooting 28, then dividing, but I wasn't getting a warn. Oh, I don't know. Good stuff right there. Good stuff. Oh, yeah, I wasn't getting, I was like, warn answer? Let's go right here. The next question. Where did it go? Here we go. Next question is, it is generally believed. We can sleuth through this one. Are the three conditions met? We can pretty much solve this one beyond what the question asks for. It is generally believed that 75% of college students, sophomores regularly recycle. So when you think about this, we're asking, do you recycle or do you not recycle? So instantaneously, what kind of question am I asking here, Cad? Just put one letter in the chat and I'll know you know what I'm talking about. We're asking, do people recycle? That's the question. Do you recycle? This kind of gives it away if I mark this. That's what we kind of believe is true at the moment. It's like a hypothesized this. So that kind of gives away what we're asking. Are UT sophomores any different from this figure? Or a researcher at UT got the corporation, blah, 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 blah. They took a random sample out of. Now, this one we don't usually mark. That is population size. We don't usually mark that because we just don't use it in the equations. That's the sample size that was taken. Correct. Categorical. Great job there, Cad. So this is population size. This is sample size. Based on the answers they provided, 84 of them recycle out of the 128. This is where people usually forget that this is x. So that's the proportion out of the sample. So now we need to take x over n to get p hat. It's all about kind of knowing what you have and knowing where to go with it. 84 out of 128. And 84 divided by 128. There's the sample proportion. That's just in our sample we observed this. And there we go. That's got it. And now we can do a lot of things here. We can do, I guess we did the confidence interval on the last test. So we can do a hypothesis test with this, and it mentions the conditions. Condition one last time here, everybody, is random. So did it say randomly selected? Well, so let's go right here, mark our conditions. 1, random, as long as it says, and randomly, we got it. Condition 2, 10%, which is what they're alluding to. So let's put this right here. Condition 2, less than 10%. And we would have here, sure, doesn't want to do it. Watch this. There we go. 128 is less than 10% of 5,000. So 5,000 is the population size, and 128, which is what we sampled, is less than 10% of the 5,000, so we meet that. And then here, when we do a test, success/failure, we need to have both NP0 is greater than 10. And it doesn't matter if it's equal to. Not a big deal. We'll deal with it if it's equal to. And Q0 is greater than 10. So to test this, we need to do NP0 because we're going to do a hypothesis test right here. P0's up there. Q0 is the complement of it. So P0 is 0.75. What is Q0? What is Q0 in the chat right here? So what is Q0? If P0 is 0.75, what will Q0 be? Or it's the complement of it. So N is going to be 128. And then we're going to times that by P0. So 75% of that. Great job right there, Kat. Excellent work. You are correct. It's 0.25. And this is 25% of that. So about 75%. So about 80. Oh, I should be able to do it in my head. I should be able to do it. Let me think. So 75. My brain's breaking. No, I'm thinking about it's like 89. I should do it more exactly in my head. Wow, that was way off. Should be able to take 3/4 of it. So divide into quarters, Brian. 64, 32. Yeah, 96. What am I doing? What am I doing? Should have been able to just cut it in half, then cut it in half again, and add the half with the smaller half. There we go. Quick way of doing it. Got to practice that mental math. But you know what we can find out in our head really quickly? 128 times 0.25 is 32. So both of these are greater than or equal to 10. I know, right? I was so sad right there. I was doing it a way wrong way. I was like, what am I doing in my head? So both of these are greater than or equal to 10. So we pass this condition right here. Excellent work. Mental math, good way to practice. How did I do so poorly on that mental math? I don't know. Okay. I was thinking like divide it into 10 parts and then add up the parts. And I was like, what am I doing? It's half of a half. That's what a 75th is. It's half and then a quarter put together. If you think just 1/2 plus 1/4. And so if you solve those mathematically for the half and the quarter, you can get it. Half, just take half of that, take a quarter of it, which is a half of a half, and you're good to go. Mental math, I love it. So now let's test this. Let's run the test. That's all we're really going to do in this question is run the test. And to run the test, we need to do the following. P hat minus P0 over P0 Q0 over N square root. So this is going to equal to, we need our P hat, which is 0.065625 minus 0.75. I'm not plugging that yet. And then we go down here to the bottom. We do 0.75 times 0.25 over, And then we do over here 128. And we square root. Don't forget square root. I've done that before. So this is going to give us the z-score right here. And we could look at how it also would be done on the test, because we're probably going to run into a roadblock here. We'll get the z-score. And there's the standard error. 625. 2.45. And we're asking, I think, is it any different? So I guess one thing we need to do is we need to see if it's any different. So let's see right here. We're asking, so we got a z equals negative 2.45. Somehow we have a magical black pen right here. So if we're asking, is it true that the proportion of students who recycle is equal to 75%, and we're asking if it's any different, the alternative is going to be that the proportion of students who recycle is not 75%, which means this is a what-tailed test. Like when I draw out my curve right here, which I wish we could have you submit drawings, like should just buy everyone a tablet and then make students submit drawings. Like, you have to draw out the normal curve and submit it. Everyone would be like, look at me trying to get my perfect normal curve. There we go. That's a lot better. Oh, there. Look at that. Perfect. That's the perfect normal. So when I draw this out right here, this is a z curve. So all z curves are the same. We can get a decent estimate of the p-value here because we're going to go right here. We're just going to go center of 0, 1, 2, 3, negative 1, negative 2, negative 3. These are just z-scores. So we just go 1, 2, 3. Negative 1, negative 2, negative 3. Now we're going to plot where we landed. We landed right here at... Oh, no. That's just one as extreme. We landed right here at negative... Good. Z equals negative 2.45. Something just as extreme as that is over here at z equals 2.45. So that's just as extreme. Does my p-value look big or small, CAD? What do you think right here? There's the p-value, and we're doing the two-sided right there. What do you think? Do you think I'm going to reject or fail to reject the null? Just visually looking at it. And I'm not trying to trick you. I'm not being like, aha, tricked you. Visually looking at this with the 0.05 alpha level, what would you think? And there's something really interesting right here because, yeah, it definitely looks small. You're right. And think about this. If I were to graph this right here, CAD, what do you think these pink areas would be shaded as? Like, how much are they of the curve, basically? And I want you to look at where I'm plotting this line. And I want you to think about this, because this is a good way to know that it's definitely reject. What do you think the pink shaded areas are going to be? Like, the pink shaded areas are probably how much of the curve about? Like, outside of 2 and negative 2 on the total tails of the curve, we would have a p-value of what if we landed a z-score of 2 or negative 2, and we did an absolute value test of more extreme then. So now the p-value right here, just the pink shaded area by virtue of seeing it, is going to be basically what? Which is when we reject the null, 5%. So these p-values we have to be smaller than that because that's 5%. Our p-values in the yellow right there are further out. Now, you should be able to identify that this is a smaller p-value. Like, if we put this on the test, I would prefer multiple choice questions for this to be like A, I'll make it bigger so you can see. I would prefer the following. Let me think, 2.5758. So it's going to be closer to, I got a guesstimate of what it'll be. I'll put it first. There we go. This is a very reasonable way to ask the question. Some of these are ridiculous. The big answer right there is completely ridiculous. Graphing this out right here, you might be between 6% and 8%, but by virtue of knowing negative 2 and 2, you would be able to eliminate, well, it has to be less than 5% because we're beyond 2. So there has to be less than 5%. We wouldn't expect you to calculate this. The fairest way to ask this on a test is a multiple choice question. But then if we wanted to, if we weren't taking a test, we could go right here. And I said it's going to be 0.008. Good, it can get that fine of an answer. Let's go to outside of And the answer is, oh, wow, I was way off. It's 0.014. I was off by a few thousandths right there, 6 thousandths. Oh, a little bit off today on that. So the answer would be right here. If we were to make this the exact right answer, it'd be that right there. So pretty close, but it's my answer rounds to 1%, and this rounds to 1%. So it's about 1%. I'd say that's good enough. My answer rounds up to 1%. Their answer rounds down to 1%. So either way, it's about 1%. If I said it's 0.8%, they said it's 1.4%, I'd say it's about 1%. But this is the exact answer. You're not meant to find the David M. Lane answer on the test. You'd be more meant to know by looking at this. Like we talked about, we know that this is about 5% of the curve. So we would know that our answer has to be less than 5% when we're further over right here. So the only plausible answer we would see, we'll go down. How many word sheets do we have open? We're only at 42. The only plausible answer would be this. Like I could see how this would be a tricky one, but this one has to be the answer because it's the only one less than 5%. Good stuff right there. That basically covers the question. I mean, other than this, we just have to reject or fail to reject the null, which should be pretty clear and quick to see right here. We reject the null. We reject the null. I hate getting random things, even if it says it's from CVS. I don't believe it. I don't believe any messages. My parents text me and they say, hey, it's mom and dad. And I say, no, you're a scammer. I know mom and dad don't text me. Mom and dad don't know how to text. They're old. One more person completed it. We're just about 2 more people away from getting the bonus points. Let's make it happen. My parents don't know how to use telephones. When my mom grew up, they had party lines. When you write here, whatever confidence interval you're making, kind of quick one on this. Whatever confidence interval you're doing, if this is a rather than doing the steps necessary, here we go. What level of alpha did you use to above detect? It should say we are at certain percent confidence. Am I losing my mind? 93% confidence. Okay, that's a 0.07 alpha then. So whatever confidence level you use right here, your alpha is 1 minus. So with a 93% confidence, it'd be 1 minus alpha for the, or 1 minus confidence interval for the alpha level. So with 93% confidence, we need to go down here, and the respective alpha level would be 7% or 0.07 alpha. So that would be good right there. A researcher believes that British men are shorter on average than the men from the USA. A random sample of 35 men from the USA, ages blank to blank, was observed for their height. The mean height was this, and the sample standard deviation was this. Meanwhile, a random sample of 35 British men was this, with an observed height of this. The mean height, the sample was this. Which type of problem is this? So we have 2 groups. We have British men and USA men. So which technique is this? This is a great question. We covered this at the end of class today with all the betting we did. So which type of question is this? Really great question right here. We've got here British men and USA men, and then we're measuring their heights. So a key thing is we're trying to analyze heights. That's very important. That should narrow it down to 2 choices. So by analyzing heights, we're down to t-tests. Now you might say, well, how do I know if it's a 1 sample t-test or a 2 sample t-test? If we just wanted to test height, it'd be a 1 sample t-test. So if I said, let's examine height, that's a 1 sample t-test. If I say, let's examine the heights of USA men and the heights of British men, then we have right here the 2 sample portion of it. And that's where the 2 comes into play. It's not 2-tailed. It might be 2-tailed. But the 2 samples come into play right here. This is 2 samples. That's what 1 sample test of a mean, 2 independent sample t-test. We 2 sample t-test. And the rule for it, or the condition for a 2 sample t-test that we do, is independent means. So there's a 2 sample independent means test. Lots of ways to configure the words, but it's basically just a 2 sample t-test. There we go. We got it. And so 2 sample t-test is being used because this is a quantitative variable being compared on 2 groups. Your visualizations for this are going to look something like the following. You've got here USA, and you've got here British, and I am blocking it. And we would go right here, and we've got the USA, and then we've got the British. And there you go. We've got here the 2 groups, and then you got height over here, which is quantitative Y variable. Excellent stuff right there. Let's look at the next question on this. Let's see what it wants us to do. write down the null and alternative hypothesis. So the null and alternative hypothesis are going to compare the means on this. Suggested by the first sentence. It says on average that it says that British men are shorter. It says on average British men are shorter, and we need to look at the jump output to see how they're doing it. Okay. The jump output right here is doing USA minus Britain. So we're going to write our null this way with USA minus Britain. Let's go ahead and take the output or take this and write the null. So one thing you can do whenever you see the jump output is just put mu's above them. Mu USA minus mu Britain. British. And we assume that this is equal to 0. That's the null hypothesis, that there is no difference. The alternative hypothesis states that British men are shorter, so that means there would be a positive difference. As in, the mean for USA would have to be higher for the mean than British. Don't know spell it. So that means the difference would be positive right here. The difference would be greater than 0 when we subtract these two numbers. So taking mean USA minus mean Britain would result in a positive difference. Like it's like 10 minus 5 is a positive difference. So the first mean would have to be larger for us to get this positive difference right here. So that's the null and alternative hypothesis. Always remember, key thing for multiple choice especially, the null has the equal sign. The null has the equal sign. So let's continue on right here. Below is the jump output. Calculate the t-ratio. Oh, we got this. Destroy this question. How do we do the t-ratio right here? We'll put our classic notes. We started office hours with this one, so we should be able to just ace this question. How do we get this t-ratio right here? Who knows how to get the t-ratio for this one? Who knows how to get the t-ratio? This is such a good one to be like, okay, boom, got it. So when we do this right here, the equation for the t-ratio is y bar 1 minus y bar 2 over the standard error, which is s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. I think that sounds about right. That sounds about right, because if you notice, this is the difference. Like that y bar 1 minus y bar 2 is the difference. The standard error is this right here. That's the standard error, just in a little longer, like fully written out. I think CAD, and great job, CAD. Excellent work. I think you've done it right there. Difference over standard. Yep. Difference over standard. Yeah. Once you see it, you're like, oh, yes, this is a difference standardized. That's all it is. You might be in the boat, CAD, where I tell people exam 3 is just a lot of practice of the same material, like knowing what a test statistic is, knowing to reject or fail to reject the null, that a lot of the chapters coincide with what you're doing. Do you feel like a lot of the material for exam 3 has been very repetitive, CAD? Do you feel I'd love to, this is the advice I give to students, and maybe I'm wrong, but I'm just like, exam 3 is a lot of repetition. It's a lot of like, what are we going to do? Look at the p-value up there. Looks like we're going to reject the null because the p-value is less than alpha. Oh, we're doing the greater than test, right? So there's the p-value we're using. Yeah, it's a lot of repeat. And remember, we're doing the greater than test, which you can literally just substitute that in here to say, do we have evidence? Or you could put it over here also. You could put greater than 0, and you can literally write mu and mu. When we have paper tests, I suggest that. I usually show students, like, I'll like use the document camera. The more you practice, yeah. I really mean it. Dave, who was a professional soccer player, had concussions, and he was like, Brian, I can't do this. I'm gonna fail the class. I can't get good grades on the tests. And I was like, we're gonna do every assignment, we're gonna do every homework, we're gonna do everything we're doing, we're gonna do all the projects, get A's on them. And then he went to the final and got like a B+ on the final and made a B in the class. And he was super happy, and I was super excited for him too. It's not hard, it's just new material, but once you learn, it's not that bad. Exactly. It's very repetitive new material. Exam 2 is probably harder because difficulty level on exam 3 is higher, but there's less material. Exam 2 difficulty level is a little bit lower, but there's more material. So I don't know. I've just seen people have exam 3, just all of a sudden the grades shift, where, you know, some people are like, oh wait, it's just the same thing over and over and over again because we're gonna low p-value here, reject the null. We have evidence for a difference between the means. There are 3 p-values. Circle the p-value. There it is right there. And we just mentioned that a moment ago because it's the greater than, because you can just put USA minus Britain greater than 0. So that's the p-value right there. If we use an alpha level of 0.01, so how do we know to reject or fail to reject the null? We look at p-value and we ask, is this p-value less than alpha? And I love these contingent questions because if someone selects the wrong p-value, that would change their answer. I hate it when we do things like that because then all of a sudden someone selects this answer and then we have to grade this one differently because, yeah. So what is your conclusion right here? So if you notice, you only get 1 point. I miss doing paper tests now, but they're so much longer to grade. Yet we reject the null. And why do you do it? You're 100% right, CAD. Why are we rejecting this null with this p-value? The null is that there's no difference. The alternative we're looking for is that USA men are taller than British men. So why would we reject? Boom, Layla right there. 50 points. Good to see you here, Layla. Exactly. And we were just talking about the repetitive nature of this, that, I mean, this test is done the same way. And just look at this. You would ace this. People are probably like, hey, Brian, can I go take this paper test? Can I go write? You know, that's all you have to write. State the remainder of your conclusion hypothesis test. Make sure you would just say, I have evidence of a difference between the difference in the heights of men. I reject the null that there is no difference. I have evidence of a difference. So just think about it like my Pearson, where it always says, like, we reject the null that there is no difference between the means of their heights. We have evidence that there is, or that men in USA are taller. Ooh, this is a fun one. This one has like 2 solves on it. This one has 2 solves. I've been working this test for like 6 years. Okay, let's do it. The following is a t-test, one sample t-test right here of a population mean. The 95% confidence interval for the mean is showing, but much of the other output is erased. The researcher wanted to do a 2-sided hypothesis test and was testing to see if 22 is the value. Okay, so what do you notice immediately about this interval? This was a good question. What do you notice immediately about this interval? What do you notice immediately about this interval? We might be able to solve it straight from that. This was a good... Yeah, we can immediately solve it from that. That actually solves the answer. That will solve the answer for you right there if you know how to then know where to go from there. There's other ways to solve it. You could find the t-statistic for this. It'd be a lot less fun. I'll find the t-statistic in the background while people use that way of solving it. The t-statistic, which this is the long way of solving it, that's the quick theoretical way, which will get you the answer. So the standard error is on the bottom. I'm going to put the equation over on the other side now because I'm running out of room there. So the hypothesized value is 22, so 24.0303 minus the hypothesized value, which is mu naught. That's mu naught right there. If you can't tell, that's mu naught. That's the mean, is the mean right there. The standard error is 0.06053. And so exactly, it doesn't fall in the confidence interval. So that means it can be rejected at the 0.05 level. I'm finding the t-statistic right here. And our degrees of freedom was 32, which means it's slightly normal. This is a long way of solving it. And so we get a t-statistic of that. Is like, was it positive 3.3? 3.35. So the curve's going to look like this. I'm blocking it. And you're going to be out here at this. You're going to be at a t of... You're going to be over here at a t equal to 3.3. And you're doing the two-tailed, so it's t of negative 3.3. You know what's interesting? I want to see how exact this p-value we calculated is. Let's go here to the t-applet. And 32 degrees of freedom. T-score. Ooh, person who made this problem, what are you doing? Yeah, I want to know who calculated that. That is they might have just went, yeah, because I think they just changed it. A little unhappy with this problem right now. The only possible answer is this one. This is the answer. And I think as Kat is pointing out right there, it doesn't fall in the interval. That means it can be rejected at the 0.05 level because anything outside of a 95% confidence interval has to have a p-value less than 0.05. So this one was chosen specifically. This wrong answer right here was chosen specifically for a reason that it's right above 0.05. The answer has to be below 0.05, which eliminates all of these answers. Since it can be rejected, every one of those answers is wrong. So see, and it says like offers no clue, even though you might not know exactly what it is, there you can figure out decently that this is going to be a very small p-value. But yeah, and wonder who wrote this one. Maybe I wrote it. Nah, my questions are not usually that complicated. It's a very good question. I just wish we put the exact p-value on there, because I mean, if someone goes and looks at, ooh, we got some type 1, type 2 error. Type 1, type 2 error right here. Okay. If we were to give a student, let's see. Yeah, okay. The interpretation one on type 1, type 2 error is always the hardest thing to grade. Okay. Let's go ahead and take a look right here. The null hypothesis, even if you don't know, there's only one answer. Yeah, exactly, Kat. That's exactly it. There's only one answer less than 0.05. So it's like, you have to reject the value at the 0.05 level. So there's only one answer it could be. So that's like the super quick way of instantaneously solving it. You don't have to draw out the distribution, find the t-score, find the degrees of freedom, worry about what the t looks like, and estimate p-values. You can be like, oh, it's not in the interval, I can reject it. So it's meant to be a really simple question that seems complicated, but the complicated solve just adds more confusion to it. The quickest way to solve it, just looking at it again real quick, is just be like, oh, the value's not in the interval. I can reject that value at the 0.05 level. So value up here of 22, not inside interval. I can reject that at the 0.05 level. Oh, there's only one p-value that's less than 0.05. They're all above. So obviously we do have information that can help us solve this. And the only plausible answer would be any p-value less than 0.05. So quick solve on that. Type 1, type 2 error right here. Classic example. I literally, this is what I always do. And then someone wrote this test question. And I was like, well, crap. Now I'm teaching to the test, because I literally in class always talk about the null hypothesis is students don't cheat. The alternative is that they do cheat. And then a few students got stoned. I was like, no, I literally did this in class. In a type 1, the null is true. I was like, no, it's literally the question I did this semester when we did this. In a type 1, the null is true. Maybe I just didn't teach it as well back then. Maybe I don't teach it well now. Who knows? In type 1, the null is true. So what does this mean right here? In a type 1, the null is true. So what does that mean? In a type 1, the null is true. It means the student did not cheat. So in a type 1 error, it's true that they did not cheat. But in a type 1, the null is true and we reject it. So you just have to remember, in a type 1, the null is true and we reject it. So we're going to reject the null. And that means we accuse a student of cheating when they did not. So that's a type 1 error. In a type 2, the null is false, but we are going to fail to reject it. So we're going to stay with this right here. In a type 2, the null is false, and we fail to reject it. Type 2, the student did not cheat, but we say they did cheat, exactly like Brian is. Thank you, Kat, right there. So 50 points. No one right there with Brian Stevens, with Don Quixote, Man of La Mancha, Scared of Them Windmills. I wish I knew. Type 1 is rejecting the hypothesis that students are not cheating when they actually are. And type 2, type 1 is rejecting the null hypothesis that students are not cheating when they're actually not. So just real quick, no. I have another, I don't know if I told this story on this, but the first time, or really hasn't been many other times, the first time a student really complained about me was because of type 1, type 2 error. Like, not like complain, but they went to Charlie and they said, I was talking to Brian Stevens in Stat Lab and he got my type 1, type 2 error questions wrong. I don't think he understands it. Like, it's so easy to reverse them, to reverse what's going on. And I may have done that. I can't recall, because Charlie actually asked me about type 1, type 2 error. Then he said, Brian, can you explain to me type 1, type 2 error? Because apparently the student was like, yeah, he doesn't get it. And I was teaching statistics. So it's pretty important to Charlie, who's director of the undergraduate program, that, and I'm glad he did that. He said, hey, Brian, a student said you don't understand it, that you got it wrong, that you're reversing it. Can you explain to me type 1, type 2 error? And I may have reversed it. I don't mind. I mean, but if your teacher's getting stuff wrong repeatedly, we all make mistakes. I just keep waiting for a review to be like, Brian can't solve problems. Yeah, it gets very confusing very fast. That's why we always say in a type 1, Like we slow it down and we use our ways of memorizing it. Since I came up with this way, I've never reversed it. It's just so easy to flip. So easy to flip in a type 1. Tell me about that null hypothesis in a type 1. Just tell me about that null hypothesis in a type 1. We're only going to talk about the null hypothesis right here. I love it when I can do this in person and be like, hey, everyone, tell me about that type 1. Tell me about that null. I want everyone to see this. I want everyone to make this right here. I want to see you're talking about this right here. What are we talking about that null hypothesis? In a type 1, that null hypothesis is what? Like, it is a what statement. Like, that is the what right there. When you look at that right there, that null hypothesis, you're going to say that is definitely what in the type 1. That is a what statement. You look at that and you say, that is what. You'd be like, that is true. So when you look at that and you say it's true, exactly, Layla, we're going to make an error, though. The error is rejecting it because it's true. It's true that they did not cheat. So the error is going to be rejecting it. And when you reject it, you're going to say, I have evidence they cheated. So, and you know what I think it is? I need to work on this. My chat doesn't appear as quickly. I think that's part of the problem because MuBot sees stuff quicker than I do. Just type the number 1 right here real quick. You'll see it in the, I'll tell you, watch, I'll do this right here. You probably already typed 1. Go ahead and type 1. I want to count, I want to time this. The amount of time it takes from MuBot seeing something to me seeing something, I'll hit it. There we go. I'm going to watch over here to see when I see this over here. That was only 2.6 seconds. And Caroline's typing 1 also. Caroline's is taking longer. I still haven't seen Caroline's over here. Good to see her, Caroline. You see, Caroline's took like 7-8 seconds. I don't know how MuBot sees things. CAD just typed 1. Oh, wait, CAD, yours didn't even go. Oh, CAD typed 1 again. I don't get it. Like, here, what? I'll let you see it. You can see the phenomenon right over here. So go ahead and watch this. Someone type 2 in the chat and we'll time it out right here and you can watch it in real time right now. So go ahead and type 2 in the chat and then we'll watch between this window and this window because MuBot somehow sees things before I do. So there we go. And then watch over here. We'll click it and we'll get a time on this. There we go. Okay, so that was 4 seconds. And then CAD also typed it. And it looks like it's taking longer for CADs because I've been talking this whole time and I saw CADs. Look at this. CAD still hasn't appeared over here. And there's CADs appear. I do not understand why that happens. So remember, MuBot, you see, MuBot can type things in the future, and we still haven't seen MuBot's thing appear. I don't know how MuBot sees the future. I don't know why it takes a while. I just don't understand how MuBot can see things I don't see yet. I don't know. I clicked the wrong button. Maybe my... No, I don't think it's your Wi-Fi. It's probably more something about mine. See, I don't even see that over here yet. I'm seeing it in MuBot. Maybe I should watch MuBot's chat. I'd be able to see things quicker, which is a bummer because I like to reply as quickly as I can to comments. Yeah, that took like 16 seconds, which is so weird, right? I don't think it's your Wi-Fi. It's storming really badly in Nashville, so everything is freezing and lagging. Maybe it is. Maybe it is, Layla. I feel like it's a YouTube thing or something, though, or Suddenlink. I didn't used to have that problem. I'd ask questions and it'd be like pretty quick, but now there seems to be a 3 to 10 second delay when I see it. I don't like that. I like to ask questions and boom, answer appears. Like when you type it, it appears. It helps with flow of conversation. I'll start looking into it and trying to figure it out. That's side mission for Brian. The fun of streaming. The fun of also being a streamer who doesn't have many streamer friends. Yeah, it could be like, I always like blame my Wi-Fi. In a type 2, the null is false and we fail to reject it. So if people didn't catch it, in a type 2, right, it's not a big deal when you ask a question, I'm not answering. Yeah. I know, right? That's why I've started to realize that because if you notice, I'll tell you something here. We'll finish this question. I'll tell you about rules for teaching real quick. We'll hop back to doing more review. Students would probably be more concerned about a type 1. If you were giving a 0 to any student who were determined to have cheated using baseline Turing method, what type of error would a student typically consider to be more serious? A student would be more scared of a type 1 because in a type 2, the null is false, but we fail to reject it. It is false that they did not cheat. So this is a student getting away with cheating. So in a type 2, the null is false and we fail to reject it. And in a type 1, the null is true and we reject it. So a student would be, they didn't cheat in a type 1, so a student would probably be more afraid of a type 1. Yeah, let me hop over to here. So one of my big things with teaching, which definitely I felt bad about because I've noticed this and I'm trying to remind myself of it, is usually I have a rule like I don't answer the questions because I hope it never gets annoying because that's not my goal with it. Is the more I answer the questions, the less class interacts. And if I don't keep this like mission that we interact, like this goal of interaction, then it goes away. Like if I start answering all the questions, if I start not asking questions, then the interaction goes away. So it's tough sometimes because I don't want to answer questions like I want, but then Cad's pointing out like I'm answering the question. I'm like, I've answered the question, and meanwhile, like, yeah, thank you so much, Cad. I appreciate that because, like if I'm just saying answers and stuff and no one's listening, I'm not. People are obviously listening right now, but if this isn't a conversation, if it's not us working together, then I can just teach everything. But with online education, I truly believe interaction helps me learn. Exactly, Kat. Exactly. And that's why I wish what you type is instantaneous, which I don't know, a month or two ago, this started happening, where MuBot can see the future. Maybe Kat's typed something that I'm seeing in the future. It forces me to figure out the answer, so I like it. Yeah. Yeah. As Layla's pointing out right there. Great job, Layla. I'm looking into the future right now. MuBot can see the future. Maybe it's with MuBot or something, but I don't think MuBot can do that. I don't understand. Yeah. I don't know. I'll look at updating the stream, but it's YouTube. See, got to make a lot of updates. Maybe I'll work on it this weekend. But yeah, no, great job. Great job interacting. I do notice the people answering questions are usually getting the material down. So don't worry. If you didn't answer questions this time around, don't worry. You've got opportunities in so many more classes. So my biggest advice, don't worry what anyone thinks. Don't worry if, like, being like, the student who answers questions. I had this guy in class who he'd answer every question. Ian was his name. Sorry, Ian. Calling you out, Ian. His name was Ian. He'd answer, MuBot is going to take over one day like Yellowtron. Yeah, he's already seeing the future. There's a problem going on right here. So this guy, Ian, would answer all the questions. He'd wear a suit to class, and he'd be like answering every question. He'd be sitting there, he'd be like, such and such, such and such, such and such. Such and such, such and such, such and such. And he and I were friends on Facebook. He was a random like friend from class. And then I saw like Ian went to law school. Ian like was doing all these things. And I realized, wait a minute. He was probably learning the material really well. He was probably making connections. So don't ever feel bad for being the one who answers questions. Because I was like, man, Ian was doing the right thing right there. Like, I wish I was the one now answering questions. I wish I was the one like, I have a question. Can you explain this? I mean, I think there's a difference if you're like interrupting the teacher. Like, you don't want to in a class be like, the teacher's like, okay, we're going to review for the exam. You're like, can we actually like not review for the exam? Because I don't want to do that. And then everyone's like, wait, what? Like, no, we're going to review for the exam. But no one's ever really had that issue in my online class. I think also because we can all talk, there's just so much opportunities. So I think that's why I like online even better. Is everyone has the opportunity. There's no, like if someone has their hand raised in class, they've kind of got the floor for the moment. But online, everyone's got kind of the fair ability to just put something in the chat, to make jokes and have some fun. I mean, I'm going to always remember from this class, William talking about it's trash. I remember the first time he said that, I was like, let's not do that. And then it just kind of came like, that's William's thing. And then today he said he loved something. It was Gossip Girls. Who would have thought that? Better than you? William, I disagree with you. Thank you so much, Kat. I appreciate that. I agree. I really like it way better. You can rewind live. We got a lot better features. We've got HD on here. Got Wacky Wednesdays. Got so many things we never even use. Do I have Batman on here?
It's not the question you deserve. It's the one you need.
Never do that button. I need to start doing that. I need to make a better layout for that one. We've had so many different ideas. I got just tons of... What other random buttons have I not hit lately? We'll go back to reviewing here a second. There's most of the random buttons there. Exactly. And that's... So Caroline points out it's a lot harder to ask questions in Zoom. I'm always watching the chat here, Caroline. Like, I've got my confidence monitor over here, so I'm always watching the chat. So I think people realize, like, whenever you ask something on here, I've got it set up for, like, a streamer setup. So the only time I'm not reading what you're writing is when I'm looking over here at the screen. But when I'm looking this way, I'm looking actually at the monitor, like I'm touching the monitor now. And so I can see very easily what everyone types. So when you type something, I'm reading it. Like I'll just watch the chat as class goes. Which I'm about to do a session to help teachers with this, because I really think you should be watching the chat at all times. And that's what people are not doing in Zoom, because then they don't treat it like a real class. They teach it like they're recording. It's all right. I understand it, other educators. I'm sorry. I'm not trying to call you out. But I think it becomes like you're just, like recording something to be broadcast later. If you're teaching a class, there's meant to be interaction. So my biggest thing is get a second monitor, put the chat on the second monitor, and learn how to, like we've learned how to take questions in class, that if you're teaching and someone raises their hand, your attention splits off into that direction. And then you have to set the expectations for your class. You have to say, okay, I'll take questions at this time, which, maybe I try to make sure that I want people to ask questions at all times, but for different classes, they might have different styles than mine. So set those expectations. Well, I'll tell other educators what to do later, and they can tell me I'm wrong. Maybe, I don't know. What is the symbol used to identify the probability of making a type 2 error? What do we got right here? Well, we're back to reviewing again. Here's the chi-squared. It's not the chi-squared. I was about to say you answer questions. Oh, thank you so much, Cad. Yeah, that's my goal. Yep. Here, we'll cover these wrong answers. Here's the chi-squared. It's chi-squared. That's the type 1 error. Let's label them. Oh, my gosh. So this is chi-squared. That's the chi-squared test statistic. No, that's not it. This right here is type 1 error. Type 1 error. This is nonsense. So I should have done these in red. This is just no. No. Anyone know what 1 minus beta is? 5-letter word. MuBot's going to look into the future here. Watch this. I'll be able to see your answer a lot quicker now. Does anyone know what 1 minus beta is? I'm watching the future right now so I can see the answer to the question. What is 1 minus beta? 1 minus beta is a classic equation that we use very quickly. I'm just going to watch people say over here. I should be able to see it. 1 minus beta is what? This equation right here is what? So I'm so trained to look over there at the chat on the other side of the screen. I have to look at this one. I've got it on the main screen now. 1 minus beta is definitely this. What does this equation solve for? I just got on office hours, so I don't know where. Yeah, we just in chapter 19 quiz here, Carly. Yep. I'm in the future watching MuBot right now. So power. Everyone says power right there. You're right, it is power. So this is power. Power is not the right answer. This is the right answer right here. We'll highlight it. Wants to know the probability of making a type 2 error. That is type 2 error. Is there a specific, Carly put in the chat, we'll probably do one more of these. Is there a specific one you want to do? We did a lot of them yesterday, but which one are you working on right now? And then we can head over. Kennedy, good to see you here. This is type 2 error. This is power. Great job, Kennedy. And Kat and Layla and Carly, good to see you here. This is power right here, and this is type 2 error. This is type 1 error. That was nonsense, just so you can see it again. Probability of not making a type 1 error. We don't use that equation. And then the chi-squared test statistic is not really related to this topic. It's just here for wrong answers. So, got to have some wrong answers. Trying to think of it. Let's go down and do the true-false here at the end. We'll end this with some true-false. Some good old, a certain story describes, yep. Does it have whether they lived or died, or does it have where they were injured? Which of the combos does it have? Does it have whether they lived or died, or site of injury? Because it's like, no, it's going to be site of injury versus lived or died, and site of injury versus what they were hit with, like an arrow or a sword. Like, which of those describes it? Because there's two versions of it. And we'll do these true falses, and we'll do that one right there. There's two versions. There's one that has site of injury and if they lived or died. The other one is site of injury and weapon. So is it weapon or mortality? One of those two things will be analyzed right there. The weapon that was used or the mortality that may or may not have occurred. One of those two things. Which version do you have of that question? Power represents the probability that we correctly fail to reject a true null hypothesis. No. Power. Correctly reject. Yep, cool. It's the lethal ones. It's the mortality. We'll do that next. You got it. Power is the ability to correctly reject the false null. Power, which we just talked about right here, is 1 minus beta. I'll disappear so we can talk about this. Power is 1 minus beta. And so with this being power, 1 minus beta, that is power, and this is 100% false right here. That's a false statement. If based on the same set of data, you change your confidence from 90% to 95%, the resulting 95% confidence interval is considered less precise. Okay, this one's tricky. When something is precise, just think about when your friend says, give me a precise time you'll arrive. You'll say, I'm going to go from 4:02 to 4:03. And your friend's like, wow, that's really precise. Could you be less precise? And you say, okay, I'll arrive somewhere between 3 to 5 p.m. Your confidence interval just got water now. So going from this little itty-bitty confidence interval to this mega confidence interval right here, your confidence interval just got way wider. There you go, way wider, I was going to say. It just got very much wider and it got less precise. So this is a true statement right here, going from 90 to 95, which is more confident, makes it less precise. I think the less precise might cause confusion because it's more confident, it's more numbers included, which is less precise. That's the idea of what less precise is that this interval is wider, i.e. less precise. And this is just increasing the confidence, which would increase the z-score or the t-score relative to a z or t confidence interval. We are going to get less precise. Very, very true statement right there. A p-value represents the probability of seeing the result you saw. Results more unusual than that, assuming the null hypothesis is true. Yep. That is a very true statement about the p-value. It's the probability of our results or results more extreme happening by random chance variation, given that the null is true. There's nothing about that that's wrong. I like to say a p-value is the probability of our results or results more extreme happening by random chance variation, given that the null is true. That is the correct definition of a p-value. The only way to decrease the probability of a type 2 error is to increase the probability of a type 1 error. What 3 ways do we have? What 3 ways do we have to decrease type 2 error, which actually would increase power respectively? We have such a good sheet on this, and it's probably around, wow. First try. We were reviewing this at the end of class today. What ways do we have? Just take a moment right here. This was a review we did in class today, talking about type 1, type 2 error. And type 2 error is your beta. Type 1 error is your alpha. That's what this stands for right here. We're into details. We wrote this out. These are inversely related, meaning as one goes up, the other goes down, but they're not complements. Power is the complement of beta, like 1 minus beta is power. So we have 3 ways, kind of. We have 3 ways of impacting. That sounds right. We have 3 ways of impacting beta, which impacts power directly because it's complement of it. The 3 ways to impact beta are going to be the sample size, as in take a larger sample. The test has less chance of a type 2 error, i.e. is more powerful. We could impact alpha, which is, it said, is the only way to impact it. No, we can adjust alpha, but it costs us type 1 error. By raising this, you have more type 1 error, which means you'll have more false positives, more results that you're saying, hey, we got results, when you really don't, as in you reject the true null. Type 1, null is true, error, rejecting the true null. Effect size we don't really control. It's just the true difference right here. Like if you have a workout that will put on 0.3 pounds of muscle every week versus a workout that puts on 12.3 pounds of muscles each week, well, it's going to be easier to observe this effect size and not make a false negative where we fail to reject the false null. Type 2, fail to reject the false null. And so this would have a more powerful test, i.e. easier to correctly reject the false null. That's what power is right here, the ability to correctly reject the false null. The 2 of these things that we can majorly impact, so let's highlight them. The 2 that we have direct control over are these, but you got to watch with that alpha because you're really doing bad statistics if you just increase your alpha, because you're just going to increase your type 1 error rate. Usually people want to use a 0.05 because that's not playing games with your alpha. So your sample size is something you probably do want to adjust, but then you run into money concerns because the more you sample, the more it costs and the more time it takes. So it is a false statement. It is a false statement that this is the only way we can impact power. We can also impact it with sample size, and we don't really directly impact it we don't really directly change effect size. We can't control the true difference. True difference is just what exists. We don't really control it, but it does impact power. It's easier to see big differences than it is small differences. In the business, so this is not included on your exam. We did mention how target, like if I had gone through this, and it's not determine loyalty. No. There's a really cool example. This would be false. This is not on your test. I removed those questions. I'm 99% sure they all should be removed because there was only one question I saw that was on there. So I removed the business analytics presentation questions. I just didn't want to speed through material yesterday. We just did chi-squared only yesterday, so that way you don't have to worry about like, hey, even though these questions right here are not meant to be that difficult, I just didn't want to burn through questions and be like, hey, we got to get through all the material. We gotta go. Because yesterday was just chi-squared, and we finished up the material yesterday, and we got to review today. So let's do Carly's question right here. We'll hop to space. Let's do this. Favorite song? A certain war story. War never changes. Go over here to the assignments. That's what I've heard. When does the new Fallout game come out? That would be amazing. Are they making a new Fallout game? 76 was like the last one. I'm gonna go. Almost got it up. New Fallout. 2021? What? No way. Fall 2022. No idea when this is going to come out. One of these days. Here we go. Let's go over here. Certain war story. Casualties. Here's the causes one. Aha. Here we go. Let's do this. So what's the keyword we look for right here? Since we're on, I don't know why we'll fix the chat up. So the keyword we look for between two variables, two words, is we want to put here independent, as in the site of injury is independent of the injury being lethal, which kind of sounds crazy. Like, would you rather get injured in your shoulder or your pinky? I'd rather get injured in my pinky. Would you rather get injured in your earlobe or your arm? The earlobe sounds like I'm getting a piercing or something. Let's get a little earlobe injury right there. I don't want arm, no. So it seems to me that these probably do have some sort of association, but the null hypothesis is that the injury site is completely independent of it being lethal, which sounds automatically like we're going to see some issues here. The alternative hypothesis is that they're not independent. That means knowing where somebody gets injured would give you information about whether or not it was lethal. So just think about when we say, where you get injured is not independent of it being lethal. Like the injury being lethal depends on where you are injured. It makes perfect sense. Like, at least when we talk about it, like, we kind of know where this is going. So when you look at the table right here, you might notice people who were hit in the limbs, only 13 of them had a fatal injury where 22 did not. That's a little bit about 1/3 fatal injury in the limb. Don't want to get a bad injury in the limb. Where body, which is, like chest area and stuff like that, 64 people out of 71, which is a much higher percent. That's about 90-ish percent, 91 maybe percent of these people were fatally injured. And in the head and the neck, oh, geez, that's like 96%. So really, really a lot right there. So yeah, we're seeing definitely some sort of association right here. And that's what it means to say they're not independent, is to say there's an association, like it gives you information. Now, this is the part where we need to go over to jump, because we can do, I think we did this one by hand yesterday, and it's just a lot of solving. We can do one of them by hand. It wouldn't take too long to do them all by hand, but it's going to be easier to solve it in jump, especially the last few parts, the chi-square test statistic. So check out yesterday's video. I did one of these completely by hand. We want to take the row total. I have 2 questions from Ken. Yeah, you got it. Put them in the chat here, and we'll do those next. So this is the formula for the expected. So it's row total times column total over grand total. And this is specifically going to solve for this one right here. Specifically, we're solving for this right here right now. So whatever this solves for, this row total times this column total over the grand total, which is always the same, is going to solve for the expected count for people who were injured in the body and had a fatal injury. Hopefully I didn't just hit a wrong button. We'll see. The answer will appear, or we will know the answer. We're going to go here to copy. So make sure to pause the video if I go a little quickly, or tell me to slow down. I'm going to here copy to clipboard, and you get this by clicking the table. Copy to clipboard, and when we copy to clipboard, we're going to hit Control or Command C. With Control or Command C, we're going to go back here to jump. You can be anywhere in jump. Oh, look, we already got some yesterday stuff. Being anywhere in jump, we're going to go here to New Data Table. New Data Table. New Data Table. See one of the questions already. We'll do that next. Great job. Thank you, Caroline. And under New Data Table, we're going to go here on the New Data Table and go to Edit, Paste with Column Names. Edit, Paste with Column Names. This is key. Make sure you paste with column names. And what you'll see when you go to Edit, Paste with Column Names under the New Data Table, File, New Data Table, Edit, Paste with Column Names, you're going to see the column names appear at the top. Don't worry that the first one doesn't have a column name. That's fine. And then you see here the counts of fatal versus not fatal. Next step, table, stack. Small for me to read right there. Table stack is going to stack columns on top of each other. Just see, I'm injured right there. Table stack is going to stack columns on top of each other. Let's go ahead and stack those columns by double-clicking the blue columns. Only click the blue columns. So now that you have the blue columns stacked on top of each other, we're going to go ahead and click OK. And so let's do this right here. We got the data ready to go. We got the columns. We got all the good stuff. Now we're going to go here to Analyze Fit Y by X. I'll pause here on this screen. Analyze Fit Y by X. With Analyze Fit Y by X, we can look at a Y variable being explained by an X variable. And very importantly, when we go to Analyze Fit Y by X, we need to make sure when we do the Analyze Fit Y by X that we put down here in the frequency, and this is where the mistake usually happens, is we need to make sure we have the count down here. This is the frequency, the count of the variable. So make sure to have that right there. It's that one, you bet. 2 questions ready to go next. And here's the output. And I think, do we have it in the same order? I'm going to click the red arrow right here. I'll zoom in so you can see. I'm going to click the red arrow. I'm going to delete all these other ones. I only want to see, you know what we can do, so we don't get confused, is we can literally only put in the expecteds. And it's flipped. Rather than dealing with this flipped, I'm going to do the following. I'm going to go to Redo, Relaunch. And since it's flipped, I'm just going to flip these right here like this. And then I'm going to go over to here and do the same process. If yours is flipped, you can just make sure you put them in, but it's better to... That was found under the red arrow under redo analysis, or relaunch. So if yours is flipped, go to relaunch and then just flip them, or analyze fit Y by X and just flip them again. This just brings back up the window you had when you go down here, the red arrow, and go to redo relaunch. Going right here. There we go, the expecteds. And let's take a screenshot of this and bring it over there. So that's got that. And let's bring it over here to this world. 56.52, we got it. 36.3, 36.62. I can't read. 27.86. 14.48. 9.38. 7.14. Oh, don't do that. Oh, come on. Always double check your numbers to make sure you didn't do a rounding error. If you get a small rounding error, just tell me. We'll fix it. But now, go through your millions of jump tables that are open, and you actually have the chi-squared test right here. The chi-squared test is at the bottom of the screen. It's the chi-squared test statistic right here, 51.02, which is ridiculously large, making an insanely small p-value of... If you hover over it, it'll tell you it. Tell us the p-value. It's Here we go. Whoops, wrong button. It's 0.000000000834. It might be hard for you to see on the screen, but it says it's 8.34 e to the negative 12. Ridiculous. 51.02. And that p-value, how many degrees of freedom? This is a 2 by 3. 2 degrees of freedom. Also check the jump output for that, but remember this is 2 by 3, as in 3 by 2 you can call it. 3 by 2, just delete 1 on each, 2 times 1, and that's how we get the degrees of freedom. Good question right there. P-value, it's 0 basically, round to 3 decimals. We should definitely reject the null, conclude that the site of injury on whether or not someone's lethal are not independent. Just so we can see that result again right here real quick. You can see it in the table. We'll do Caroline's questions right here. You can see in the table that people who were injured in the limb were more likely to have a not fatal injury, where people who were injured in like the head and neck, high probability of fatal injuries. And so, yeah, that's what we have right there. If we do the row percentages, you can actually see the percentages, which is kind of cool. That's why jump's neat. Yeah, so the people who were injured in the body, 90%, I said about 91, and then head and neck was 95, and then about 1/3 there, a little more than 1/3. That should do it. Yes. Would it have accepted? I don't think it should accept that. Oh, it does accept that. No way it accepts that. No way it would accept that. I don't like that it accepts that. It's basically 0. I guess they're doing it for anyone who doesn't calculate it. It's like we showed. It's 0.00000000000834. It's ridiculously small. It is about 0. Which means there's strong evidence of a difference, or strong evidence that they're not independent of each other. I was thinking of 2 sample means for a second. The results of a chi-square test for independence concludes color choice is dependent on gender of a kindergartner, which of the following is true. I haven't done that one lately. Let's go take a look at it. Here we go right here. It's a result of a chi-square test of independence. We'll go grab. Load. Oh, Canvas, don't be weird today. And great job, everybody. Oh, Canvas, don't be slow. Don't be sad, Canvas. Don't do that. Preview. Really? Wow. Okay. Found it. Let's do it. Here we go. Here we go. Let's check it out. Here we go, Caroline. Here we go. Okay, so the result of a chi-square test for independence concludes color choice is dependent. So what does it sound like we did here? If we conclude that the color choice is dependent, well then, what would that mean? The gender of a kindergarten causes. Ooh. That's an instant no right there. Yeah, no, you got it. Yep, that's actually it. You are 100% correct. Because when it says the null hypothesis is that they're independent, the alternative would be, you can say that they're dependent. But that means we had a lower p-value than alpha. It means we rejected the null. So if we conclude that they're dependent, then that means we rejected the null. And actually the chi-squared test statistic would be larger. Just kind of look at that. When you have a larger chi-squared test statistic, so here's the chi-squared test statistic, a very, very small chi-squared test statistic will make a large p-value. But as the chi-squared gets larger, the p-value gets smaller. So you can see right here, chi-squared's getting larger, p-value is getting smaller. Sorry, it blinks right there as I do it because I'm trying to like do it quick enough you don't see it. Do that. So small chi-squared test statistic, and here's it getting larger. You can see as the chi-squared gets larger, the p-value is getting smaller. Oh, it gets ridiculous there. So the larger the chi-squared, the smaller the p-value. So it'd be very false to say the chi-squared is very small because we know the p-value is low. So the chi-squared had to be... This answer is just ridiculous to say it's very, very small. No, I don't know how large or small it was, but it can't be very, very small because that would result in a higher p-value. But we can't have had a higher p-value because we have a lower p-value because we showed evidence that there is an association here, or that they're dependent on each other. And then the next one was, in fall, 39 students reported being, whereas 59, 39, okay, liberal and conservative students. Let's find out here. Let's check out this one. Preview. We'll find this question. Where is it? Where is it? I saw that one earlier. Great job, Caroline. Excellent work right there. Now we're just going to see that one all the time. Up. Here we go. So the null has the what sign. The null has the what sign. What sign does the null have? Like automatically, you'll know instantaneously. I'll put the future view on with MuBot. The null has the what sign. I see the future right here with MuBot. The null has the what sign. Equals. Great job, Caroline. I'm looking into the future right there. The null has the equal sign, so that eliminates this answer right here. Answer C has to be eliminated. So now we're asking basically, is there a difference? It doesn't really say like which way it wants the difference to go. It just says, you know, like looking at this right here, we're looking at the mean, social views, political views. So you use the jump output. Are there differences in the score? So it wants to know about differences in the scores. It doesn't indicate which way we're going. So what do you think? A, which has the does not equals, which is one of our choices. B, which has the greater than. This one's eliminated because this has no, not happening. Or less than, which would indicate like the less than or the greater than would indicate very liberal is higher than very conservative. The less than would indicate very liberal is less than very conservative on average. So where do you think we will go with this alternative? It is A. Great job right there, looking in the future. That's got it. Excellent work. Is it making more sense, Caroline? Excellent work. Good practice. Large values of chi-squared test associate. No cause and effect. We don't do that here. The degrees of freedom are 5. 1, 2, 3, 4. And those 4 degrees of freedom. And lower p-value power is lower than alpha. I guess got it. Hopefully I didn't misclick anything. And let's go down here to the bottom. Awesome. Great job, Caroline. And 499 point. Not going to get one wrong. You ready? Oh, wait. What is the corresponding alpha level? Really? Really, you going to do this right here? You're going to do a crazy interval? There you go. I'm not messing around with this. Corresponding confidence interval is 1 minus alpha. We're not messing around with that. Boom, 10 out of 10. That's the way we like to do it right here. Not messing around with that confidence interval. Crazy confidence interval right here with the 94.7% confidence interval with a corresponding alpha level of 5.3%, or, you know, just make sure it says right here, enter in as a decimal, so do that. If you get one of those things wrong because it says enter a decimal, just tell me about that too. I'll be like, okay, sorry about that. We'll fix it. Well, that's got it. We're done. We'll play sad ending. Well, everyone, excellent work. Excellent mini term. Lot of hard work. A lot of people have 20, 30, 40, 50 hours of watching class live in 3 weeks. It means in 3 weeks. And think about this. The amount of time you put in to class. I just want you to see how much it's paid off, because there's 3 people right now. There's people with very high grades. And it really, I think it's the interaction. I want you to carry this moving forward in your life. Like, in 3 weeks, there's a lot of A's and B's in this class. And I'm very proud. I'm very proud of all the hard work. Yeah, that's the amount of time we've been live on the channel. So, and there's a lot of people who are up there. There's a lot of people. And everyone learns differently. Everyone has their own way of learning. And if this worked for you in this class, if you did something that works, I want you to carry it forward, because, I got to ask the question, who thinks we should get a cat? Should be like, Brian, you should get a cat, or no, you should not get a cat? Because someone very near and dear to me had a way of learning material. And when they went to a different part of their education, they said, here's how you should learn material. And they tried it. They switched up what they were doing. But they had a way that worked for them. So if you have a way that works for you, when you find that way, keep with that way. And when you find better ways, start incorporating those better ways. It's all we're here to do is just learn throughout life. So if I'm going to end with one bit of advice, if you did well in this class, then just keep doing what you're doing. Carry this over to other classes. Bring the positive attitude. I'm going to play my favorite. We'll end with something more upbeat. We'll end with this. We got to go with a happy song ending right here. So, if what worked for you in this class worked, do it in other classes. Made A in this class, you're welcome, Layla. That's what I want to see, is just people realizing like there's a formula for success, and usually it's dedication, hard work, and asking for help. That's what will lead to success. So with that, feel free to swing by any office hours. I'll be seeing everyone really soon. I think we're getting those 2 points on the final. Awesome news. You're welcome, Caroline. You're welcome, Layla. I'll see everyone later. If you have any questions, please email me. Take the test. If you're stuck, let me know. Bye for now. Bye, everybody. Bye, Puppet Shark. You're welcome, Cad. Bye, everybody.